Hey everyone, welcome to the videos for section 2.4 in the textbook talking about existence and uniqueness of solutions. So this section is going to be a lot more theoretical than the stuff we've been talking about for the last couple days, but this is something we kind of have to go into. So the point of this video is to say what the theorems are that we're getting towards and why they actually matter in the case of trying to actually solve problems that we're going to do with the rest of the course. So let's go ahead and jump on into that. So like I mentioned, we're talking about existence and uniqueness theorems, which is, the title of this video up above. And the point of this video is what the theorems are and why you should care. So let's start with the second one of those, why you should care about these theorems. So the first reason you should care about these is because the idea of the theorems is that there is a solution and there's exactly one solution. There aren't multiple solutions, and there's not the case that there's just no solution at all. And ideally, you want your problems to have this property. Why? Because physical situations have this property, right? If you throw a ball in the air, something happens, and only one thing happens. It can't randomly do one of two different things. There is only one possible outcome. So, since physical situations that we're trying to model have this property, we want our model for it, our ODE, to have the property as well. And the second way to use these is along the same vein. But if you're working on an ODE that's supposed to model a physical problem and it doesn't meet the criteria for the theorem, it probably isn't a great model because of what described above, right? If you're trying to model a physical situation that only has one solution and your ODE can have multiple solutions at the same time, it probably isn't a great model for your problem. So it gives you an easy way to say, okay, this model doesn't work, or it lets you know that, okay, this model is going to stop working at a certain time. So by that point, I have to stop considering this model because things are going to start breaking down and I can't reliably predict the flow of the system beyond that point in time. So violating the conditions of the theorem means you're probably not a great model. And the third thing to think about, and this is something that'll come more in handy as we try to solve problems and sketch curves for it, is that uniqueness results tell us that solution curves cannot cross. Although this really only holds for first order equations. Why is that the case? Well, if you have two solution curves crossing, let me draw a sketch of something up here for you. Some ODE, and I have the red curve that does this, and the blue curve that does this. So they cross over at a point. Now let's rethink about this problem again, but use that point where they cross as our initial condition. Right? By its uniqueness, it shouldn't matter where we put our initial condition. We'll get the same curve no matter what. So let's think about that intersection point as our initial condition. Well, then what happens? Then we have two solutions, the red and the blue, that solve the same ODE and have the same value at that intersection point. That means that by uniqueness, they have to be the same curve, but these two obviously aren't, so that violates something's going wrong somewhere. And the thing that goes wrong is you cannot have solution curves that cross. If two solution curves cross, they had to have been the same curve the whole time because of uniqueness theorem. So this, it turns out, will be a big thing when we start drawing pictures and looking at all these models that we're looking at. Solution curves cannot cross. And that's the main way you want to be using the uniqueness part of the theorem when we start moving forward into the rest of these sections. All right, let's go ahead and now state these two theorems. We'll state there's two of them. There's a linear version and a nonlinear version. We'll state them both and then go over sort of what they're saying. I'll just write them up on here on the board, and then we can talk about what they mean in a second. All right, so here is the linear theorem. It says if the functions p and g are continuous on some open interval a to b, contain t0, so t0 is going to be my initial condition point inside ab, then there exists a unique solution. Here are the important words here. There exists a unique solution. Y equals phi of t that satisfies the differential equation y prime plus p of t y equals g of t for all t in the interval, and it has any initial condition you want. You can pick y0 to be anything, satisfy the initial condition, and solve the ODE. So in particular, when we look at the other one, we'll see the comparison. I get this for all t in AB. Actually, I get this for all t in AB. So P and G were continuous on A to B, and I got a solution for all t in A to B. So as long as P and G are continuous, we get solutions and we're happy, and solution curves can't cross, things like that are all great. All right, now I'm going to write up the nonlinear version, and we'll talk about that one briefly too. All right, so here is the nonlinear theorem. So we have similar assumptions. We are assuming that f and df dy are continuous within some rectangle. So in this case, we don't have that, like before we had p and g were just functions of t. Now f and df dy are both functions of both t and y. So I need them to be continuous in some rectangle. They pick Greek letters. I'll just stick with their notation, but it just means that there's some rectangle, but t between alpha and beta, y between gamma and delta, where my function's continuous. And that rectangle had better contain the point t0, y0. Then in some interval, t0 minus h plus h, we get a unique solution again. So we get the same result here that we have a unique solution, but some of the stuff is different, and we'll be going over the differences between these in the next video. But for this one, we just got the statements of the theorems. Basically, if you have the proper things being continuous, namely p and g for linear functions, and f and df dy for nonlinear equations, then you get unique solutions to some extent. And we'll talk more about the specifics as to what the differences are between these two and why that matters in the next video. All right, thanks for watching this one, and we'll see you in the next one.